Okay, today we start on chapter 13, vibrations and waves. Vibrations and waves are a very important part of physics. We see them throughout. We see them in the orbit of the planets around the sun. We see them in the orbit of the moon around the uh, Earth. We see, as you can see in the figure, you see ripples on water. Those are wave formations. You have earthquakes have seismic waves. They have two different types of waves, an S wave and a P wave. We'll understand what that is when we get to that section. But let's start off with Hooke's law. Hooke's law is what the experiment that we're gonna do on Thursday. So here we have a figure of a spring. We're gonna have to assume a frictionless surface. uh, this block is sliding on a frictionless surface, so the friction doesn't slow things down. That's a whole another area, but we'll get started with this figure here. Let's imagine a block attached to a spring moving on a frictionless horizontal surface. If the spring is stretched, or compressed a small distance x from its unstretched or equilibrium position and then released, it exerts a force on the object, as you can see in the figure. In 1678, Robert Hooke performed experiments using springs and found that the spring force, F of S, F sub S, obeyed the equation shown, Fs equals minus Kx, where x is the displacement of the object from its equilibrium position, that is x equals 0, and k is a positive constant called the spring constant. This is known as Hooke's law. The value of K is a measure of the stiffness of the spring. Stiff springs have large K values, and soft springs have small K values. Notice the negative sign in the equation. It means that the force exerted by the spring is always directed opposite the displacement of the object. In the figure on the left, the block is to the right of the equilibrium position, so X is positive and F of S is negative. This means that the force is in the negative direction, to the left. In the middle figure, the object is to the left of the equilibrium position, so X is negative and F sub S is positive, indicating the direction of the force is to the right. Of course, when X is equal to 0, as in the right-hand figure, the spring is unstretched and F of S equals 0. Because the spring force always acts toward the equilibrium position, it is sometimes called a restoring force. A restoring force always pushes or pulls the object toward the equilibrium position. Let's say that the block is initially pulled a distance a to the right and released from rest, as shown in the figure on the left. The force exerted by the spring pulls the block back toward the equilibrium position. So X is decreasing, which means the magnitude of the force is decreasing. The block gets faster as it moves towards X equals 0, and its speed is a maximum just when it passes through the equilibrium position. The middle, as shown in the middle figure, momentum causes the block to overshoot the equilibrium position and compress the spring. Now the block is moving to the left of the equilibrium position, where the values of X are negative and the spring force acts on it to the right. The force increases the further the block gets from X equals 0, and its speed decreases. The block finally comes to rest at X equals minus A. The figure on the right then accelerates back towards X equals 0 and eventually returning to the original position at X equals A. The process is repeated and the block continues to oscillate back and forth. This type of motion is called simple harmonic motion. Simple harmonic motion occurs when the net force along the direction of the motion obeys Hooke's law. When the net force is proportional to the displacement from the equilibrium point and is always directed toward the equilibrium point. Not all periodic motions have the same path, can be classified as simple harmonic motion. For example, think of a ball being tossed back and forth between two people. The ball moves repetitively, but the motion isn't simple harmonic motion because the force acting on the ball doesn't take the form of Hooke's law. Okay. Think about the object suspended from a vertical spring. Its motion is simple harmonic. In this case, the force of gravity on the object stretches the spring until equilibrium is reached and the object is suspended at rest. By definition, the equilibrium position of the object is X equals 0. When the object is moved away from equilibrium by a distance x and released, a net force acts toward the equilibrium position. Because the net force is proportional to x, the motion is simple harmonic. Okay. Here are three basic concepts which are important when we discuss any kind of periodic motion. First is the amplitude. The amplitude A is the maximum distance of the object from its equilibrium position. In the absence of friction, an object in simple harmonic motion oscillates between the positions x equals minus a and x equals plus a. The period t is the time it takes the object to move through one complete cycle of motion from x equals a to x equals minus a and back to x equals a. The frequency f is the number of complete cycles of vibrations per unit of time. Frequency is the reciprocal of the period. As shown in the equation, frequency equals 1 over t. Conversely, period t equals 1 over f. We can use Hooke's law and Newton's second law to find the acceleration of an object moving in simple harmonic motion. This equation for the acceleration is an example of a harmonic oscillator equation, which gives the acceleration as a function of position. Because the maximum value of x is defined to be the amplitude a, the acceleration ranges over the values of minus ka over m to plus ka over m. Okay, the next section, we're going to talk about elastic potential energy, but I might do a demonstration with a little video.